I'm starting to record the meeting. We're super happy to have Ana Maria Rey here, and Professor Marino asked me to give the introduction so that I don't have to do it. So I am very happy about this. Please, Tamir, go ahead.
Thank you. Thank you so much, Harvey. So welcome, everyone. I'm delighted to have this opportunity to introduce Ana Maria, with whom I had the pleasure and the joy to collaborate since now 4 years, since the time in which I was a postdoc at JILA. And when you end up writing, let's say, the introduction to someone, you typically go to the major achievements. And some people working in quantum simulations may know Ana for realizing SUN magnetism with ultra-cold alkaline earth atoms. But the fact is that it's very difficult to compress her career in just a few achievements. So the situation is that at the moment, I think it's fair to say that Ana Maria is the beacon for theory at JILA. So she's the key partner of several important experiments there. Jun Ye, John Bollinger, James Thompson, really ranging across a broad variety of platforms that go from optical lattice clocks, cavity QED, trap diodes. And actually the list continues with experimental collaborators outside of JILA, Joseph Tyson and Francesca Ferraino in Innsbruck, to mention a few of them. So you really see that Ana Maria, let's say, embodies this role model of having a theory close linked to experiments. Essentially, in her own words, sometimes she says that her life she couldn't imagine her life without experiments. Nevertheless, she even reached out to condensed matter. Some of you may know some works that she has done with a lot of nice theory collaborators as you, going from Leo Radioski to Victor Gurari on optical lattices and on other topics that are more condensed matter related. And so he has really, let's say, a broad span on many body theory from AMO to condensed matter. If you are interested, let's say, in a more canonical introduction, I mean, you can check our Wikipedia page, which is partially what I did, but the few coordinates that maybe you want to know is that actually she was born in Colombia and studied there and did a PhD in Maryland in 2004. And after 3 successful years as an item postdoc at Harvard, she started at JILA. She has a number of very remarkable prizes. Maybe among those I would like to mention, in 2013, she got a MacArthur Fellowship, which is an extremely prestigious prize in the US. And today we are very glad to have her here, and we thank her for waking up so early. And please, Ana, you have the floor.
Oh, thank you, Jamil, for the very kind and generous introduction. It's really a pleasure for me to be here today speaking as the Quantum series. Unfortunately, well, it's via Zoom, but hopefully still we can learn about the discussion today. Well, what I wanted to use this opportunity is to tell you about recent developments in trap ion simulators, but also give you a general overview. Hopefully I can convince you that these systems have great potential to help us understand many body behavior for quantum simulation. And at the end of my talk, I want to tell you some developments that we have recent, trying to push these systems towards potential sensors of dark matter, and maybe in the future they can help us unravel the mysteries of the universe. So with that, let me start my presentation, and I checked that it was working, and now it's not working. It's not moving the slides. What is going on? Let's see. Okay, now can you see my second slide?
Yes,
Yeah.
yes, it works.
Okay, great. So let me start just emphasizing the goal of the research that I do. That I think what we want to do is really to harness the behavior of quantum many-body systems and use these systems for many different applications that can range from quantum information to metrology. And for me, what is fascinating is to understand how complex behaviors can emerge just from their basic constituents and their interactions. So try to bridge the very complicated gap between the behavior of few body systems that we understand to the emergent properties of many body behavior, and try to use the techniques that we have in atomic, molecular, and optical physics, try to actually bridge and shed light on how this complexity emerged. And our disposition, we have the fact that ultra-cold atomic systems feature were understood microscopic. Basically, we can write the Hamiltonian in a piece of paper that actually describes the behavior of the system. But not only that, but in the Hamiltonian, we have parameters that we can tune in the experiment with wide degree of control. And moreover, this can be changed dynamically during the course of experiments, and we can access the time evolution, the quantum dynamics, without, for example, the need of ultra-fast probes. So, and I believe we have done great job towards this goal. And in fact, the impressive accomplishments that we have done in our field, what is happening here, are revealed by the large number of Nobel Prizes that we have had in the last few years. I'm showing here a table of the 11 Nobel Prizes since 1997, and I mean, Bill, we have the version that we have Bill attending the talk today here. So we have seen, we have developed the control tools in order to manipulate and harness atomic molecular systems with quite degree of capabilities, and that have led, for example, to use atomic physics systems as the leading platform for state-of-the-art sensors. I like how, to show this displays this cartoon from Dave Wineland's Nobel lectures that tell us, well, it's great. I mean, in fact, we have been masters of the control of independent atoms, and that have led us to great progress. But actually, one of the goals that we have now that is a little bit more complicated is trying to not only control many body systems, but control the conditions when they are highly entangled and correlated, and actually deal and understand the fragility that you start to open when you make the particles entangle. So that's what we are trying to do in these trabium systems that I'm going to tell you today. And one of the reasons that we believe dealing with correlated quantum matter is so important and exciting is because it can open the door to various tasks that at the heart of quantum science. So we want to use correlated systems to actually build what we call quantum simulation and try to use, for example, these systems to emulate the behavior of electrons in real matter, in real quantum matter systems, but I push them to generate even better materials, so most advanced materials. Or we can try to build the foundations of quantum computers and actually reach the ideal of quantum supremacy. Similar concept of quantum supremacy can be, for example, applied to sensing, and we want to build sensors that actually surpass the capability that we can achieve with just classical particles, so highest precision and accuracy, and hopefully at the highest density. And finally, we want to use these systems to actually bridge one of the most important gaps that we have now in physics, that the connection between the microscopic and the microscopic. For example, try to understand a little bit more of quantum gravity, black holes, and dark matter, that has been one of the biggest questions that we had in the last couple of years. But I mean, what I find really exciting also is that a simple system, unique system that is trap ions, I believe that can shed light into all these different directions. I have to have a disclaimer that the talk here is going to focus mostly in two-dimensional crystals trapped by a penning trap, as I will describe. I'm not going to talk about linear traps. So there have been very nice reviews. For example, I'm highlighting one specific one. So I mean, if you are interested in linear traps, maybe you can go there. But today is going to tell you about penning traps. So although my group is a theory group, actually we enjoy very close collaboration with the experimental group at NIST that has the penning trap is John Bollinger, and well, the results that I'm going to show you today is taken by the very nice group of postdocs and graduate students, and of course all the simulations, numerical simulations that I also going to show you has been done by my theory collaborators, a fantastic group of postdocs and graduate students. So with that, let me start and introduce you the system at hand. There is we use a penning trap to actually confine beryllium ions. The system consists of a stack of two-dimensional electrodes that generate an axial confinement, and then we have a very strong magnetic field generated by a superconducting magnet. The field is as large as 4.5 Tesla, and the idea is that in the presence of rotation, that they have a set of quadrupole electrodes to introduce a rotation in a charged particle in the magnetic field that is rotating actually first a Lorentz force, and this Lorentz force is used to provide the radial confinement. So the axial confinement can have typical frequencies around 1.5 megahertz and the rotation frequency about 180 kilohertz. So the important point is that with these conditions, we can stabilize two-dimensional arrays of ions that can, depending on the frequency of the rotating wall, we can change it from 20 to up to 300, we even push to 500. They form a triangular lattice because they want to minimize the column repulsion. And you can see here, these are real images taken in the experiment where the dots actually are the trap ion system. Now, in order to generate our qubit, what we use is the two lowest hyperfine states of beryllium ions that at this very strong magnetic field are split by approximately 100 gigahertz. So, but under this splitting, we can use microwaves to actually introduce single particle gates or between these two internal states that the experiment have developed such that they can reach almost 99.9 fidelity in manipulation of these single particle circuit qubit gates. So that's good, that's one of the first ingredients, but of course we want to make these ions talk to each other. And in particular, we are interested in, for example, generate spin-spin interactions. At the distance that we have the ions in the penning trap, the separation that is more than microns scale is going to be too large so that actual exchange interactions from the column repulsion can lead to something significant. So instead, in order to induce the interactions, what we use is we introduce a set of lasers. In this case, we use pair of Raman lasers that are separated by a bit node frequency mu. These generate a moving lattice that we serve to excite the phonons in the crystal. Basically, what we have is that we can control this bit node frequency nu, and with that we can impart a spin-dependent force by controlling the proper polarizations and frequencies of the lasers that we use, and engineer this type of Hamiltonian that you can see here is just a force that is a time-dependent force on the ions generated in such a way that a spin up and a spin down particles experience the opposite force. So you can see here, this is reflected by I have the sigma c operator that is, of course, have different sign for up and down particles coupled to their position. So the important point is that if each ion is not independent because of the column interactions, and instead, as I said, they form the crystal, and therefore we can control the position of the ions is coupled to the rest and actually set by the normal modes of the crystal. And in particular, we are interested in this talk on the axial modes, axial drumhead modes that I try to show here in this figure. I'm trying to show you a little bit of animation. Let's see if it works, where you can see that we have this different set of normal modes, the axial modes being the center of mass, the one that has the highest energy, because there is not column screening. All the ions in the center of mass move collectively up and down. And well, in this cartoon, I mean, you see boundary effects, but they are minor. So the crystal is using up and down, and then we have other set of modes that actually then we can excite by controlling the frequency of the bit node mu that we have here. So for this talk, we are going to actually set the bit nodes such that we only excite the center of mass. So we are going to place ourselves very close to the center of mass bit mode in such a way that the other modes are very far from I mean, they are detuned and therefore so large that we don't excite them, and the only one that we worry or we use is the center of mass. And the parameter that matters for us actually is the detuning between my bit node nu and the frequency omega 1 of the center of mass mode. So now, if I'm going to rewrite this Hamiltonian in the rotating frame of my mode, what I have is two terms. The tuning from the bit node, set by omega. This A is going to be now the annihilation operator of a phonon in this center of mass mode, and then the coupling term, the force. You can see that I change from sigma c to this collective operator SC, and the reason is that when we excite the center of mass mode, all the ions participate collectively, so we don't have to sum individually, but instead we have a collective operator here, SC, that acts as a big spin. So I'm just going to think about having a large spin, and you see that the only part that is that because I have many ions, this is reflected by the fact that I have an square over root n here, and this is just because the harmonic when we are looking, we were replacing SC, and therefore remember that harmonic oscillator length is proportional to a square root of the mass, and because we have n particles, then we have the square root of n here. Well, but now if you stare at this Hamiltonian, you can see clearly that what I'm writing here is an harmonic oscillator Hamiltonian that is displaced. And in this case, the important part is that the displacement is proportional to SC. So if you have one particle is one up and one down, you can clearly see that the displacement is then opposite. So I'm trying to draw this here, is a trap harmonic oscillator that is displaced to the left or to the right, depending on your spin. So in general, of course, spin and the phonons are coupled, but also note that if I start with a wave packet that is at the center when the phonons and the spins are not correlated, as a function of time, what is going to happen is that I'm going to have there is going to be oscillations that at time that are periodic with the tuning, then the center of mass and the phonons and the spins decouple again every time that is commensurate with this detuning. So as a consequence, so if when I rewrite the Hamiltonian in these B operators that are the displaced operators, and you can see that there is a time where the spins and the phonons decouple, then at these specific times I can measure the spins and the phonons separately, and the only part that I care is the evolution of the spins that the Hamiltonian says by the collective operator JSC square. So we are going to focus for the moment in the decoupling points and just consider the spin part of the Hamiltonian, that is a collective one-axis twisting model, as I will tell you more details. It's a collective Ising model. Okay, so as I mentioned, we were interested in developing entanglement in these systems. So what we are going to do is that we start with an uncorrelated state, let the ball under this Hamiltonian that is actually quite simple, and then try to see if we can generate a highly entangled state and see how entanglement build up in the system. And well, I'm going to try to understand in some degree some typical tools that we have learned from quantum information to quantify entanglement. So the actual protocol that we use in the experiment is called Ramsey Spectroscopy. That is a tradition for atomic clocks, and basically is kind of understood as a quench, where I start with all my spins down. Then I apply, this is the block spheres where we have all the spins down, pointing down, or spins up, pointing in the towards the North Pole, a superposition in the X direction. I apply a pi half pulse that is coherent. I introduce coherences between up and down. My block vector is in the equator, and then I let the system evolve during my Hamiltonian that we are going to discuss the dynamics. And then in order to characterize the dynamics, I'm going to apply a second pulse at the end. So the important part here is that I'm interested in the transverse components of the spin that is during the dynamics. And this transfer component of the spin, as I said, I can infer by actually applying a second pulse that actually translates coherences into populations. So basically what we are interested here is the length of the block vector, for example, in the equator, that is given by the expectation value of by this operator, the length along X and the length along Y. Interestingly, for the initial conditions, the length along Y is always 0. So actually the length along S is the only one that provides the dynamics. So I want to understand what is the amplitude of these oscillations that happens during the dynamics that is proportional to this contrast C. Okay, so this is the measurement that I'm going to use, and well, that's what the experiment sees. So I start with a very long spin pointing along all the atoms along the X direction, and then if I look at the dynamics of Sx, of the magnitude of Sx, what the experiment sees is that if I start with fully polarized, then as a function of time, my spin is depolarizing, is shrinking, the length of my spin is shrinking, and actually this is because I'm getting entangled with the rest of the atoms. And when I measure Sx, then I'm just cutting this information because I just having a single particle observable, and therefore I'm losing it. And that's what happens if I measure the contrast as a function of time. I see that the system depolarizes. So our system is not perfect, and there is some light scattering that happens as a function of time that reduce even without interactions the contrast. But we can see that what we can do in the experiment is that we can change the number of particles, and we can contrast the different behaviors. So you can see the behavior of 21 particles up to 144 particles, the blue, and you can see that actually the 21 particles decay faster than the 144. So there is as I increase my number of particles, I make the dynamics, the decay a little bit slower, and actually this system is very integrable, and actually I can analytically compute what is the evolution of my Sx, of my contrast, and actually is a function that is a cosinusoidal function elevated to a power n with a rate that actually depends on J, the coupling constant, divided by n. So the important part I want to mention here is that I rescale the dynamics according to this formula and change the time by because of this n in the exponent, and here this n in the denominator in the argument. If I scale by square root of n, you can see that I can collapse all the curves into the same behavior. That is nice. So we are seeing kind of the dynamics that we wanted to. So, and I was mentioning that in fact this time of depolarization in some degree is because the system is becoming entangled, because one particle started to talk to the rest, and I'm losing the information when I measure. But actually, we wanted to have a little bit more quantification of actually that in fact you are generating entanglement. And for that, well, we typically look at not one body operator but two body operators, and the consequence of the Heisenberg uncertainty relations. So if I have a spin system, I cannot measure the three components all simultaneously. And in fact, if I have a spin pointing along the x direction, we can see that along the perpendicular directions, that is the y and the z direction, then I can, if you compute for even for a coherent spin state, that is a product of all particles pointing along x, and you try to compute what is the variance of y and z, you know that the variance is going to be proportional to n, so the standard deviation proportional to square root of n, and this is the standard quantum limit that is actually equally distributed along the two directions. That's the case for an uncorrelated coherent spin state, but actually we can actually entangle the spin and make what we call a spin squeeze states, and actually we can go to a regime where the noise along one quadrature is reduced respect to the noise along the other quadrature, and this is characterized by what is called a spin squeezing parameter that measures the variance of the spin along one direction, the minimal variance, compared to the length of the spin of the total spin, and what this quantity, the spin squeezing parameter, is actually 1 for uncorrelated coherent states, but reduces below 1 when I have entanglement. So this is actually demonstrated to be an entanglement witness, and also a signature of the utility of a state for metrology. What happens is that this is the type of states that I start to prepare during the evolution. So if you look at what happens with my system, I have what is called this Hamiltonian is the collective Ising model, is known as one-axis twisting Hamiltonian. And the simple way that I can understand this twisting is that, as I said, I start with a coherent state. But if you try to look at a mean field picture of the evolution, you factorize the evolution of this, and you are saying that you are introducing a rotation that depends on the value of the expectation value of a c, that we can see simply in this case because it's a constant of motion. The important part is that if you look at the noise back part of the noise of the coherent state, you can see that the North Pole and the South Pole are evolving the fastest because they have the largest component of a c and in opposite direction, and therefore as a function of time we start to twist my distribution and generate a narrower component along mostly the c direction as a function of time. And this is actually what we try to do in the experiment, where we try to look at 2-point correlators, and then we can compute we can see what is the direction at which the variance of the spin is smaller, and we put it as a function of time. The dots are experimental points. This is for a system of 86 particles. So the dots are the experimental points, and the solid lines and the theory line that follow very well the experimental. There is some uncertainty because of the measurement of the angle of the distribution that they had in the experiment. But overall, what we nicely see is that in fact, not only my spin is depolarizing, as I was mentioning before, but the spin is, we are developing a spin squeezing, and we get up to approximately, we can infer up to 6 dB of a spin squeezing in the experiment. You can see at the coast as the other quadrature start to become broader, and therefore we have larger variance. So this is a plot where are the record levels of spin squeezing in that we have achieved in colatoms, and well, we are not at the 18 dB records, but we still are here, and we are operating with just smaller particles. So that's great. So we find a way that maybe this can be useful for future for measuring small frequencies. And now let me tell you a little bit more about, well, we have isolated the ions, the phonons, and perhaps the one key ingredient that we want to start to do is not only worrying about the spins, but I want to also understand a little bit the behavior of the phonons in the crystal. So not measurement at spectroscopic times. So, and also maybe we can add a little bit of complexity in my system by adding a transverse field that doesn't commute with my Hamiltonian. So under these conditions, actually we go back to the Hamiltonian that I have, and actually we realize that just by adding the transverse field, we implement what is called the Dicke model, that is a conic model in quantum optics that actually studies the coupling between a large spin and an oscillator. So this Dicke model was introduced by Dicke in the 50s, so long time ago. And well, he predicted that this model was interesting because it exhibit a second order phase transition, for example. And even though it was introduced and generated great theoretical interest, it was hard to implement in experiments, and actually it's only recently that has been implemented in cold atoms. For example, there has been experiments using an optical cavity that have implemented the Dicke model using a Bose-Einstein condensate and using momentum space states as an effective spin degree of freedom. Actually, yeah, there has been a lot of developments. I was very impressed by all the developments that have happened this year in the demo meeting. For example, all the great developments that have happened in the Dicke model. There has been also some implementation in cavity systems with the spin 1 particles, but we were able to actually realize this model with trap ions. And I'm just going to briefly tell you that, for example, we have been seeing the evidence of this second order phase transition. So basically, as I mentioned, the Dicke model has a ground state phase transitions as I change the ratio of my transverse field. So there is a critical value. If I look at the energy of the state, the energy distribution changes at a critical value. And at this point, this describes when the coupling is strong, B, then I have a normal phase. And when I have a weaker coupling, I enter what is called the super radion phase. So in the normal phase that I have a strong transverse field, and where the critical value it's set actually by G squared divided by delta. Actually, what happens is that above the critical value, you can see that the spins want to point along the x direction, and in this case, the expectation value of a z is 0, and therefore I have vacuum in my phonons. So the ground state is a paramagnetic state with no phonons. But on the other hand, this is here, as c is equal to 0, as go to a very larger, I decrease my coupling constant B, the transverse field. What I see is that I go to a state where the system wants to be ferromagnetic, pointing along the z direction, or my plus or minus z direction, and I am going to have a macroscopic population of the phonons. That's what is called super radiant state, that I have a large population of the phonon proportional to n. So this state is entangled, and therefore what we wanted to explore is this transition between the normal to super radiant phase. And what we did in the experiments is just to decrease this is done by microwaves, but the discrete effective transverse field as a function of time. Start with an eigenstate of the large B, that is a paramagnetic state with no phonons, and go down and try to explore the phase transition, that at some point, at the critical point, there is the gap closes, and when the behavior happens, and I use another order parameter, expectation value of SC, or the product of SC times the alpha 0, the number of phonons an approx of the number of phonons in the crystal. So in this case, what we start with is large B, start to decrease and ramp down it. Of course, we don't start in the ground state. Unfortunately, there is a finite population, but we start with this state. Then we start to decrease slowly the ramp. We cannot be very slow because there is light scattering, but try to do it as slow as we can until we go to the other state. and the other phase. And in fact, we see that in the experiment. This is the distribution of the magnetization along the z direction, and you can see that in the normal phase we just have MC equal to 0 populated, and then as we go to the other phase, that depends on the ramps that we do. Sometimes we do an exponential ramp of the transverse field or a linear ramp, but at the critical point that we expect, then we see now the formation of a bimodal distribution. And actually, we look at the theory, we can see that the theory reproduces very well the normal to superradian transition, and then we are happy that we can benchmark that actually we have created actually the Hamiltonian that we wanted to create. I mean, the Dicke model has been simulated. Okay, so we see that we have control of the spins, we have control of the phonons. But now I was telling you that also we wanted to touch base a little bit and try to explore fundamental physics with the trap ion system. And well, if you look at one of the biggest questions that we have now about fundamental physics is actually the origin of dark matter. We know that the dark matter occupies 85% of the matter in the universe, and we know that exists because of some gravitational evidence, but actually at the moment we don't know what it's made of. I want to make a disclaimer that I'm not an expert in dark matter at all, but what we know is that well, it doesn't we don't understand what it's made of, and we want to understand what could be possible candidates. And actually the Axion has been proposed as a possible candidate of dark matter. The Axion actually has the advantage that it could resolve some of the mysteries of the in chromodynamics, in quantum chromodynamics, the charge and parity broken symmetry. But one of the important parts that also is appealing from the Axion is that actually it talks to us in the presence of, because it talks to electromagnetic matter. And the Axions in the presence of a very large magnetic field actually can be converted into photons. And these photons, we actually are typically, for the frequencies that are relevant, are actually in the microwave domain, and we should be able to actually detect these photons. And that has been one of the biggest push that of detecting dark matter in not big experiments, in tabletop experiments. And for example, there are the new experiments that are using superconducting qubits towards the detection of the Axion. I'm going to so for example, there are these IDMX, the Abracadabra, that try to really use, for example, in this case, microwave cavities or superconducting qubits in order to detect the photons. And one of the questions that we have is that we can try to use trap ions actually to sense also, to look for Axions. And then the reasons is that, as you know, in the experiment I mentioned, we have a very strong magnetic field. So maybe we can use that, and if we are sensitive to electric fields, maybe the electric field that we detect can actually come from dark matter. So that's our idea, try to build a sensor of electric field and displacements, and then maybe we can understand if these can be used for Axion or dark matter sensing. So at the simplest level, what we know is that we want, if there is a weak resonance force that is interacting with a mechanical oscillator, then it's going to generate a small displacement of the oscillation, and this displacement is the quantity that we want to detect. And for that, we use a complementary degree of freedom in order to detect it. So in this case, in our case, the mechanical oscillator that is going to have displacement, that feel the displacement, is the center of mass motion, and the system that we want to use to measure the displacement actually is the collective spin of the system. So as I explained before, we have the Hamiltonian that has the phonons, the center of mass motion, that are coupled by the lasers to the spins. So the important part here is that if you are going to sense displacements, then again, if you use you prepare your system, your oscillator in a classical state, like can be the vacuum of a coherent state, you are going to be limited by the standard quantum limit of displacements. But on the other hand, if you, in this case is the vacuum fluctuations. But now if we want to entangle my phonons, then in that case, I should be able to sense the displacement at a better, much better. And that's our idea. We want to try to use entanglement to better sense this displacement. So what is the idea? We go to resonance, and the reason we go to resonance is because if we are at red resonance, if the frequency that I want to detect is resonant with my oscillation, then I'm going to be more sensitive. So I'm going to go to zero the tuning, and then I have this Hamiltonian that couples the oscillator with the spins. But actually, this is not the best way to try to understand the dynamics, because in this way the spins and the phonons are coupled. So maybe it's better to write a superposition of spin and phonons as this quadrature. So you can see here, this is a superposition of SC plus A Daga and SY or JY and A minus A Daga. So these are the X and the P components of the phonons, and this is an effective quadrature of the spins along the Z direction or along the X direction. So when I write my Hamiltonian in this way, I can write it as X squared plus minus X minus squared, and you can see these are decoupled now. And actually, if you stir up your Hamiltonian, this Hamiltonian is well known to generate two-mode squeezing. That means I'm generating a squeezing separately in each of the two quadratures. So the basic idea is that if I prepare an initial state that is pointing along the X direction with zero phonons initially, then I let this system evolve through this operator, through this Hamiltonian. I'm going to have a highly entangled spin phonon state that is squeezed. So actually, a picture helps more than actually the math. And what I start is I have a decoupled spin coherent state, and in the oscillator I start in the vacuum. This is the two quadratures, the JC and the JY quadrature, and the P and the X quadrature of the oscillators. They are separate. Then during the evolution they couple, and maybe I instead go to the P and X minus and the P and X plus quadrature, and you can see that in fact, if you look at the Wigner function, there is a squeezing going on in the two quadratures separately. And then if I try to apply a displacement of the phonons along then because the phonons, I am going to apply a displacement. In this case, then what happens is you can see that the displacement happens along the X minus and the X plus direction. So I just displace slightly a little bit my oscillators, because it's along the narrow quadrature, then I'm very sensitive to that. The only issue is that the spins and the phonons are coupled, and then I measure the spins. Then I'm going to destroy all the back action, the entanglement is going to destroy my sensitivity. So measuring the spins when I have this state will not work. So instead, what we need to do is I have to find a way to decouple the spin and the phonons again. And magically, this can be done by actually undoing the Hamiltonian. So applying minus the Hamiltonian that I can do by applying a pi pulse and the Hamiltonian again. So I unsqueeze, then my spin and the phonons are decoupled them. But interestingly, after doing this operation, because I have the displacement before, then the net effect after the undoing the dynamics is that the spins and the phonons become decoupled. But not only that, so the phonons are displaced, but the spins feel a rotation that is proportional to the displacement. So by just measuring the rotation of the spin in the spin degree of freedom, I should be able to measure the displacement, and that now I am immune to what happened with the phonons. And then I get the displacement in terms of just measuring the spins, because it will manifest in a simpler rotation, and I'm going to be insensitive to noise in the phonons, such as thermal noise. So that's great, and this is the results of the experiment. So this is the sensitivity of the displacement as a function of time, and you can see that, I mean, these are theoretical ideal curves, because of the entanglement between the spin and the phonons, and I can decrease my sensitivity as a function of time. There is some light scattering. This is the purple line that actually makes the sensitivity, well, not as good as I wanted to, but it's not too bad. But you can see that we are much higher than the standard quantum limit of vacuum fluctuations in the phonons, and even from thermal fluctuations, because we start with a thermal state, but we are more sensitive than that because of the entanglement. But at the end of the curve, you can see that we start to deviate from the ideal case. And the reason is that in the experiment, they have center of mass fluctuations. So from one shot to the other, actually the frequency of the phonons is not exactly the center of mass. There are some fluctuations of we cannot make this delta completely zero all the time. There is some fluctuations that happens at a frequency between 20 to 60 hertz. And therefore, you can see that if we try to undo the dynamics, unfortunately, we are not undoing this delta part. And therefore, we cannot close the loop. And then we become open a little bit to thermal fluctuations and also to entanglement between the spin and the phonons. So this is what our main limitation. But even with that limitation, we reach a sensitivity that is 8.8 dB below the standard quantum limit. And more impressive, it's going to be 19 dB below the thermal bound. That is what we had. And being sensitive of displacement as low as 36 picometer per root hertz. Then the point if we want not to send displacement but an electric field, maybe what we want to apply is the drive for very long times. So that's why we're doing these experiments, and just for simplicity, compare with what happens if I just not do the undo and apply the Hamiltonian, the drive, and undo the Hamiltonian, but I apply the drive and then use the spins to measure the displacement. And in this case, you can see again that in this case, this quantum, because the displacement is as a function of time, the standard quantum limits goes like 1/4 divided by t squared. T is the time I drive. And still, we are performing better than that, much better than the thermal bound of my system. And with that, the important point to emphasize is that I reach a sensitivity of electric field. So the electric field is associated with this displacement eta. Here I can complete this eta with a value of electric field that is 240 nanovolt per meter per root hertz. That our sensitivity at frequencies that is 1.6 megahertz, just to compare with, instead of the Rydberg sensors that of course operate at different frequencies, but we think that we are better, a little bit better, although of course we are talking about different frequencies. And just to finalize, because I see my time is running late, so what we have done is we have been able to use the entanglement between the spin and the photons to sense displacement as low as 36 picometer per root hertz. And that is 8.8 dB below the standard quantum limit. We have been able to do electric field sensitivities that is 240 nanomoles per meter per root hertz. And the important part is that the limitation is not fundamental, are just technical center of mass fluctuations. But if we improve them a little bit by a factor of 10, we expect that the next generation of experiments should be able to detect not only 240, but 10 nanomole per meter per root hertz. And just to convince you that this is enough to actually start doing compatible searches for axions and, for possible, also hidden photons at frequencies that are at the center of mass, frequencies that is between 10 kilohertz to 10 megahertz. So just to convince you that I'm not an expert on this at all, but the point is that when you try to understand the effect of the axion, you modify Maxwell equations in the presence of A, the axion field, and this A is proportional to the dark matter energy density, a square root of that, and the mass of the axion, it should be compatible with the frequency that we want of the center of mass modes that we want to sense. So if we have an external field B, you can see that the field generated by the axion, the electric field, the photons that are generated by the axion have this form, where here B is the magnetic field that we have, that is the order of 4 Teslas, R is the volume at which the magnetic field extends. And of course, the mass is 1.6 megahertz in the current experiments, that it's about 6.5 nanoelectron volts. And if we do the calculations, the algebra, and try to see for the sensitivity of 10 nanovolt per meter per root hertz, we are going to have a sensitivity of the G, that is the coupling between the axions and the electromagnetic field, that can be as low as 10 to the minus 9 giga electron volts, inverse electron volts per root hertz. That means if we average over a day, we should be able to reach sensitivities of coupling constants as low as 10 to the minus 12 inverse giga electron volts. And if we look at the recent measurements of the Avada Kedavra experiment that actually are targeted with using LC resonators with the same frequency, this plot is small, but all we want to say is that they are reaching this type of sensitivities, 10 to the minus 11, for frequencies that are compatible with what we have. So in principle, our sensitivity is slightly better after 1 day of averaging. So still many things to go improve in our experiment, but just wanted to say that is compatible. And with that, maybe I'm going to skip this part and just tell you that I have showed you that we have been able to generate the spin squeezing in the spin degree of freedom, that we have been able to demonstrate that we can control the spins and the phonons, and maybe that we have been able to actually use this coupling not only to see a phase transition, but we also have been used this to generate a spin phonon entanglement, and maybe this opens a path for next searches of dark matter sensors with trap ions. And well, we have some way we wanted to try to start looking at individual ion addressability, and maybe in the future we can use these systems also for actually quantum optimization. But with that, let me thank you for your attention.
Wow, what a nice talk. Thanks a lot for this. I'm sure there are plenty of questions. And why not start with Dima, who is going to say exactly what I want to say, but I'll let him do it.
Yeah, thanks so much, Ana Maria, for this great talk. And what Arne means to say is that I think there are many ways that axions, for example, can interact with particles, and one of them is they can affect the spin. See, I knew what he was going to say, that they can directly affect spins, not through generating electric or magnetic fields, but act as a quasi-magnetic field acting on the spins. And the question is, will the system also be sensitive to such quasi-magnetic perturbation, and how can one compare?
Yes, you are talking about with the nuclear spins.
Yes,
you are talking
exactly.
about,
Yes.
Yeah. We thought about that. Maybe in principle we can change our ion. In this case, we have an real electron spin, but maybe you can change the system. What about if you change the system with a strontium or other ion that it has no electric spin but nuclear spin? That's interesting direction. It would be great to talk more about that.
Yeah, because our experiments that we do here, they are exactly of this type. We try to detect that. And for this comment that we need nuclear spins, generically yes, but there are some versions of axions that should interact also with electrons, axion-like particles. So even electron spin could be interesting. But one has to look at the numbers and see how it compares with other methods. And the frequencies that you mentioned, they are actually in the range that we are also interested in. So it would be very interesting to compare the notes on these.
Yes, that would be great. We have been reading your papers, of course. I didn't mention, as I said, because it's different coupling. It's the nuclear coupling, not this coupling. But definitely, this is a direction that we would like to learn more about. And if the systems can be compatible for that, that would be great. Yeah. So yes, at the moment we are just looking at sensitivity to electric field, trying to imitate what it's doing in superconducting qubits. That was kind of the most natural connections, but looking at a little bit more connections, that would be great. So in contrast to one of the disadvantages that we have is that, for example, the abracadabra experiment is sensitive to magnetic fields that are generating by the axions. We are and they're we are sensitive to the electric field, and the suppression is worse because the volume enters linearly for them. For us, it enters quadratic. So there is an extra suppression that we have because we are sensing the electric field, not the magnetic field. But if there is something that we can try to be more sensitive is to the magnetic field, that could be interesting for us.
Mm-hmm. So that this factor will not enter in the experiments where in the direct interaction with the spin. There wouldn't be this.
That's great. Exactly. That's great. Mm-hmm.
Great, thank you. There's another question, another three questions. Next is Bill Phillips.
Yes, Anna, that was a lovely talk. My question is also about the Axion search, or the dark matter search. Now, I don't know anything about this, but the idea, if I've understood correctly, is that if there are dark matter axions, then you apply a field, and this will create these microwave photons, and then the drumhead mode of the 2D ion crystal acts as a narrowband detector.
Mm-hmm. Exactly.
Now, what I'm wondering is the frequency that is generated depends on the mass of the axion, which you don't really know. I mean, you've got guesses, and
Yes.
you've got a narrowband detector. So it seems like you're really looking for a needle in a haystack here. That you've got some narrowband detector trying to see. So if the axion happens to be the right kind of thing, you'll detect it, but otherwise you won't. Have I understood correctly?
That's completely true. And in principle, well, we can tune in the experiment the frequency of the center of mass mode, and there is a tunability between 10 kilohertz and 10 megahertz. But it has to be tuned experiment to experiment. So yes, in that respect, we have this problem. But notice that this is the same problem in my understanding of superconducting qubits that use a microwave cavity.
Sure.
Because they have the cavity that they have to change the length that is resonant for the cavity. So it could be interesting if there is a way that I mean, we have more frequencies in our system. It's not only the center of mass mode, but we have other drumhead modes. Maybe the problem is that the coupling is weaker, and because it's not completely uniform. So it could be interesting to see to what extent we can generate a more clever technique that we can use the full drumhead spectrum to detect it. And that's an excellent question, and maybe future direction.
And how narrow band is the response of the drumhead?
Well,
or what's the Q? Perhaps it would be the better way of saying it.
Yeah, I mean, the Q of the center of mass mode is 10 to the 6 because there is no decay. But I mean, the frequency, so that's perfect. That's why it's no damping at all.
That makes it very sensitive, but it also means that you're only looking at a very narrow band.
Yes.
Now, if you apply this field and you get these photons, these microwave photons from the axions, then that's what drives the drumhead. But now, and you're going to look for a long time for these things to integrate up. And the idea is that you were describing what happens if you apply this force, for a certain length of time. But now the axions, at least I imagine, the axions are moving past us at something like what our velocity is through the Milky Way or something. Is the drive coherent, or is it essentially
the coherence time seems to be very long, so that's not a problem for the very long quantum wavelengths that we are measuring. So seems that the orientation of the electric field and the coherence time is not a limitation for us. That's what I understood.
Okay, but I'm not really understanding why the photons generated from these axions should be coherent.
Yeah, well, at a given frequency, I mean, so in what sense, I mean, what we are generating is a an electric field that has the frequency of the quantum of the axion. I mean, Bill, I'm not an expert on that,
Yeah,
but
me.
what I understood is that I mean, maybe Dima he knows more about that, but my understanding is that the coherent times of the actions at this frequency is long enough that for the experimental duration of, we are going to repeat the experiment many times, so it's after 1 second it's still okay, and we repeat the experiment more and more. That's our hope, but I think I should learn also more about the actions, and this is something in my to-do list.
Okay, thanks.
The axions have the same Q of 10 to the 6 conveniently, the same as these modes. Yeah, they have a Q factor of 10 to the 6.
Okay, and what sets that? How do you?
It's
virial velocity in the galaxy.
Yeah, it's what.
I mean, it's like. Okay,
yeah, go ahead, Arnie. Go ahead.
I mean, it's assumed that axions are basically a thermal gas of plane wave modes in the galaxy that are extended everywhere and have a certain frequency and random phase. And then, however, the mode occupation number is so high that you end up with something that oscillates very coherently.
So it's almost like a condensate, you're saying?
Yeah.
No, well, I mean, there's always, we always debate whether it should be a condensate or shouldn't be a condensate. It certainly has a very high occupation number of the
there is a very
okay.
simple. There is a very simple picture. You can say that the oscillation is at the corresponds to the energy of the axion, and most of this energy is mc squared, the rest mass. But there is also an mv squared over 2 term, which is random. And you said that this velocity is typical velocity in the galaxy, and that happens to be 10 to minus 3 c. So that 10 to minus 3 squared gives you 10 to minus 6, and that's so this whatever you get from the motion is a small part of the Compton frequency.
Okay.
All right.
Thank you.
There's another question by Professor Hemrich from Hamburg.
Okay, hi, Ana Maria. Thanks.
Hello.
Actually, I have a question concerning the second topic, quantum simulation on the Dicke model. I was wondering, with your ion crystal, how does that compare with the prospects of that using cavity systems?
Yes.
Is there anything that you can do that cavity people cannot do?
Yes, that's one big difference is that the coherence time of our phonons is very long. So in cavities, you always have the dissipation because you have cavity loss. And maybe you are always trying to solve for an open system typically. So the transition that typically have been probed in cavity systems is an steady state solution. So it's because you have the cavity loss, and you are dealing with an open, it's the open dissipative Dicke model. So if you look at the Esslinger, always they have to write a master equations in order to try to write what is the critical point. That is only slightly modified by the cavity losses. It's not too much, but there is a small shift of the critical point because of cavity loss.
So Ana Maria, how are the numbers? Like the lifetime of your phonons compared to the cavity photon life?
In the cavity, in our case, we don't worry about that. It can be hundreds of seconds, 200 seconds. It's very long. They don't decay. The center of mass will have a Q very long, very Q to 10 to the 6. So for us, the experiments the most important decay rate that happens is because of light scattering that can happen at the order of 200 milliseconds, so it's 500 inverse seconds. So it's the single particle. The most important source of decoherence is in the decoherence of the spin, dephasing of the spins. So that's one of the biggest advantage that the phonons for us live very long, and that's something that we can see. So maybe instead of trying to look at steady state solutions, we can look exactly at the unitary dynamics for very long, well, up to the spontaneous, the defacing of the spins. That's one of the, I think, difference that we see in the cavity implementations. And the other, perhaps, maybe you can say that there are cavity systems that now also have, but in principle, I show you the Dicke model with a single mode, the center of mass, but we also have the possibility to actually talk to more modes. If we are going to be a little bit farther the tune, we don't talk only to the center of mass mode, we started to talk to the all the different modes of the drumhead modes of the crystal. So it's going to be a slightly more rich than what you can have in the cavities. Although the cavity system has also its own tunability. I mean, you can tune, they're done with Raman transition, so you can tune different type of I mean, lately they are involving both not only the BC, the zero momentum, and the finite momentum, but they're also involving two internal states of the rubidium atoms, or I mean of the atoms. So I would say, for me, the difference is that we don't have losses on the photons, on the phonons in our case, and we can use different type of the drumhead modes. But I mean, each proposal has its own advantage, and this implementation have its own advantage and disadvantage.
Okay, thank you.
Great. Thanks for all the questions. Maybe I mean, Dima hasn't said everything I wanted to say, so maybe I can just add that. So it's, of course, again, about dark matter and the Axion-like particle dark matter. I mean, like what you're looking for is like the phonon coupling. What we are looking for is like the fermion coupling, where it looks effectively like an oscillating magnetic field at the constant frequency. But and that's what I had to think about. Axions, I mean, they are invented to solve the strong CP problem, and they are also inducing oscillating electric dipole moments. So oscillating electric dipole moments, we published a paper recently last year. They drive electric dipole transitions, for example, or magnetic quadrupole transitions, and maybe you can actually see something like this in your setup. And maybe Dima can comment on this, because I mean, those are ions, right? So I'm not sure, how does it go with the
I know that Eric Cornell, he has his EDM experiment, and in principle he's trying to look at that. He has a very important. I mean, the molecule that he uses for the experiment is very good for trying to sense for these induced time dependent dipole moments. Yes, I mean, we have not thought in that direction. We thought that Eric and other people have better experiments for doing that, but molecular ions that have very strong internal electric field. But
I mean, yes, those are great experiments, but they are looking at very low frequencies, right? So what is currently a bit of an unexplored parameter space in this whole Axion business is, I mean, like you have at ADMX frequencies is a few hundred megahertz to gigahertz, right? But they're, well, this is micro electron volts, but there's a bit of a window up to milli electron volts. And when I saw your 120 gigahertz or something like this, there are very small amounts of experiments that can actually look in this range. So maybe it's interesting to look into that.
I see. Okay. Well, I mean, we are open to. I mean, we don't know too much about Axion, so we are just in a learning curve. So it would be. I mean, yeah. If there is a way that we could contribute, that would be interesting to see. Yeah, it would be great to talk.
Yeah, your hand is raised. I don't know. Bill also raised his hand. Your hand was raised. My hand, I lower my hand.
I had my hand lowered and then I raised it again.
Okay, then Dima, go ahead.
I'm just wondering, what about somehow the extension to three-dimensional systems and also to Paul traps? Is it possible?
Yes, well, I mean, John has in his list to do in the next couple of years try to do three-dimensional crystal. I mean, independent trap is possible, and he thinks that in principle he can get and push the sensitivity to 200 particles that we have now to 10 to the 6. I mean, that's one of his dreams, and it's not crazy. He generate a stack of 2D planes and generate this crystal. So that helps a lot. I mean, we have at the moment the noise from is scales like a square root of n, because we are measuring the spins. So if we go to 200 to 10 to the 6 can be 3 orders of magnitude gain in the sensitivity. To pole traps, in principle, yes, although they don't use necessarily, they don't have this strong magnetic field. I mean, it's different. So maybe hidden photons and other type of systems that doesn't require an electric field. But of course, again, hidden photons is limited by the penetration. I mean, by the screening, by the shielding that, and then the shielding will also suppress. That's why we are not very good for hidden photons according to our calculations, because there is a shielding effect, and for the parameters that we put in our system, the shielding is quadratic again, and doesn't make us as good as other experiments for hidden photons. But Dima, I mean, as I said, we are trying to explore this direction. So I mean, we know that three-dimensional crystals definitely should work. We can increase the magnetic field a little bit, or we can increase the region of the magnetic field present in the system. This could boost our sensitivity up to 10 to the 4, 10 to the, or 4 order of magnitudes more. But if there is others, I mean, if we, as you said, if we are sensing electric fields, if there is a possibility to sense instead magnetic fields, maybe that's better, and that could be interesting to explore.
Great, thanks. Maybe before we have Bill's question, I can advertise next week's seminar. It's going to be given by Sylvia Viola Kuzminski from the Max Planck Institute of Science for the Science of Light in Erlangen, and it's going to be about quantum magnonics, quantum optics with magnons, so a bit of a different thing. Yeah, and Bill, you have another question.
Yes, Anna, could you go back to the slide where you showed the improvement in decoherence with root n and all the things collapsing onto the same
yes,
the same curve?
For the spin squeezing, yes, Bill?
Yeah, I think that's what it was.
Before the spin squeezing, for the magnetization.
Yeah, that's right. Yeah, it was earlier.
Yeah, I think, sorry, here.
There we are. That's the one, right? Okay, so first, looking at the line that is labeled decoherence. So that's now if I'm remembering correctly, this is looking at the contrast of Ramsey fringes. Is that how you're getting this information, right?
Exactly.
Okay, so now, so what is that upper line, the one that is very slowly?
The upper line, yes, this upper line is because, unfortunately, there is dephasing in the experiment because of the, I mean, we are using an optical dipole force that is a Raman transition. Then you are going to couple to the excited state, and then there is a Rayleigh scattering. Rayleigh is our dominated part, and then unfortunately, then as a function of time, the Ramsey contrast decays with this rate. So this is the bad part. So this is happens even if we have one particle. It's a single particle decay rate, and then we want to understand how actually the elastic part changes. So what we are showing is that even if when the system has this additional small decay, when we take into this gives you e to the minus gamma t basically. But it's multiplying by the same rate, is independent of n. So in that respect,
right. So so that part is not really affecting very much these other curves because it's relatively small.
Exactly.
Okay, so what is causing the decay on those other curves?
Yes. what is causing the decay is that you have this ion is talking to the rest of the ions. Yes, I have an ion and is talking to the rest of the ion. And a way that I see it, well, there are two reasons. The one physical picture that maybe you like it more is that you have this spin squeezing happening, and we are wrapping around the Bloch sphere. Yes, so our system is wrapping around the Bloch sphere. So Sx, the expectation value of Sx, start to decrease because it's not just you have a system that is going to have a more complicated behavior than what you are seeing, something an infinite. It's not there is a curvature, not a plane, and therefore as a function of time the noise is introducing a decay of the contrast. The way that I see it too, that I don't know, maybe it's the way, is that you have one particle that is talking with the rest of the ions. Yes, and then you are measuring, when you measure Sx, that is, then you are like introducing a measurement of one of the system. Sx is the density matrix of one ion, and then you are tracing over the rest. You are tracing over the rest, and because this ion is talking to the rest, when you trace over this, you are removing information. And Sx, if you compute the reduced density matrix of one particle, is just this, is just Sx, and that's why you decay.
Okay, but then you get a slower decay with more ions. That's one of the beautiful features here.
Yes.
Now, it seems a little counterintuitive because often when you make a squeeze state with many particles and a high degree of squeezing, it becomes more fragile, and this becomes less fragile.
Yeah, and the reason is just the factor of 1/n in the coupling constant, because the point is that you can you see my mouse here, Bill? No. So the coupling constant, I mean, let me go back one step before. It depends on how you normalize here. In cavity systems on BCs, you don't have J divided by N. Yes? We are normalizing by N. So because this is J divided by N, the time, I mean, maybe you can say the more particles, the more mean feel like behavior. Yes. So when you have a spin and you make on this matter, you're telling the larger your spin, the more classical. This is this idea. The larger the spin, the more classical.
Okay, good. Okay, good.
Thanks.
Okay, Dima, you wanted to have another question? Or is your hand still just raised? Dima, you're muted.
Sorry, I forgot to lower my hand, but I do actually have another question. So since you are talking about spin squeezing and then you still say square root of n, so it means that you are somehow not in the Heisenberg limit, right?
It never, yes, unfortunately, spin squeezing never give you to 1/n. The maximum squeezing that you get with the one axis twisting is 1 to the n to the 2/3. That's what you get, because again the curvature of the Bloch sphere unfortunately doesn't allow you to reach the 1/n Heisenberg limit. Yeah, you have to do something else to try to get it. I mean, if you do the time reversal of the Hamiltonian as we try to do, apply the squeezing, apply the rotation, and do the dynamics, then you might saturate the Fisher information by doing the dynamics, and you could be able to reach the 1/n.
All right, I don't see any more questions, but most people have already left. So if there are not any more other questions, maybe we can go back to doing other things as well. So thanks a lot again for your super nice talk. Thanks for getting up that early.
Thank you very much for the invitation. Thank you very much. It was my pleasure.
It was very interesting, very stimulating. Thanks so much. Bye-bye.
Thank you.
Goodbye.
Bye-bye.
Bye-bye. Thanks.